My name is Ruihang, and with How together today, it is great pleasure for us to introduce our recent work called PithTrain, which is a compact and agent-native MoE training system. And we are students from CMU, and let's get started. So we first want to introduce the meaning of pith. I'm not sure how many people knows, but pith, one of its meaning is the white tissue in some of the fruits, but the other meaning is the essence of something. So by naming this project as PithTrain, we really want to show that how we can capture the essence of MoE training and build such a system. And let's start with why we care about MoE in the first place. So if we look at basically like every frontier model that is shipped in the last 2 years. I guess these 2 weeks there are more open source models. They're all like mixture of experts. It's become the default architecture for frontier language models for quite a few reasons. First, you get more capacity per flop. And the reason is because only a fraction of the parameters are active for any given token. And this will directly translate to, say, cheaper reasoning at the inference time, which actually matters a lot in the reasoning model era right now. And the hardware has also caught up with like larger and larger memory to hold all these models in the HBMs. And at this point, there is like basically an industry consensus that doing MoE is the way for us to scale. So if we made a deliberate we are making a deliberate bet to focus on this MoE specifically because we believe that this is the mainstream going forward. So, okay, the next question is, if we want to train MoE models, we definitely need good infrastructure. And what people use in both industry and academia right now is those mature production frameworks, such as like Megatron or DeepSpeed. And of course, these frameworks have the very good model coverage. They have a good feature coverage. They're very efficient, well optimized by many experienced engineers. They're also robust. They have very large communities that exchange ideas, feedback frequently, and they're also backed by big technology companies that keep investing in these projects. So, if you want to train an MoE model today and you want the training to be fast and also reliable, this is the default option. And their adoption actually goes deeper beyond simple pre-training or fine-tuning, because a lot of like reinforcement learning post-training frameworks use Megatron as a default trainer, as an example. So Megatron is not just a training framework, it's kind of becoming a foundational dependency for a whole ecosystem that's built around it. But while we are actually using these frameworks day to day, we realize that there are still some frictions. When we're talking to people, many folks share same experiences. For example, if we want to learn how a particular technique is implemented inside the framework, or you want to set up the environment on a brand new cluster, or a fresh iClear or Neuros paper that just come out proposing a new architecture, and we want to support the architecture in the framework. In order to do these things, we need to dive very deep into the very large system. And of course, this is doable. That's like how we have been doing so far. But every time we do this, these tasks, um, there is a real cost because we need to dive into it, and they can add up. And we try to think about like where these frictions actually come from, and it seems to be a quite like few structural things. Um, they have massive code bases, which is like well over 100,000 lines of code. There's also heavy C++ extension dependency under the hood, and there are many layers of abstraction stacking on top of each other. These are all overhead for humans. Human engineer has to like read all the code, trace through the abstraction, and also rebuild the extensions. But now in 2026, increasingly the entity that doing this work is probably no longer a human, and instead it's the coding agent. Um, AI for coding has actually gone from autocomplete a few years ago to very powerful agents in this recent few years. They evolve very quickly, and almost all of our development tasks are right now done through agents. We are typing prompts or even speaking prompts instead of like doing coding anymore. So the agent has become the primary user or developer of these mature production frameworks. And coming back to the frictions we mentioned before, it's true that, say, we can leverage AI agents and completing a task with agent is much faster than a human could do. But this does not mean that the underlying problem is solved. The source of the friction has not changed at all, and the friction still exists. For example, for an agent, 100,000 lines and the abstraction layers mean the agent has to do far more file reads and also far more analysis just in order to orient the agent itself. And also, the C++ dependency means whenever something breaks, the error may appear at, say, somewhere opaque in the extension, or the backtrace may come back and forth across the language interfaces. So that leads us to this central question. Can we have a framework that is more friendly to agents without giving up the production grade speed? And of course, a framework that is more friendly agent is typically more friendly for agents as well, for humans as well. So, in order to answer that, we first have to check how we have been evaluating a training framework so far. Traditionally, people focus on the performance, which is the golden metric. Uh, it's basically the purely the training efficiency with metrics like throughput and MFU, and this is very easy to understand because if you have faster training, you spend less time on the training, and it also means less money. And everyone optimizes framework based on this axis. But when we say we want to build something that is more friendly for agents, we found that like it's very vague actually. Like, what does that mean? So we first tried to give it a name, which we call agent task efficiency or ATE for short. Previously, it didn't even have a name. And this is the second axis that has been completely missing in the past. The idea of agent task efficiency is that we take the same task and we let an agent to complete it on two different frameworks A and B. If the agent completes it more efficiently on A, we say A has better agent task efficiency than B. And here the word efficiency is actually measurable. We can, for example, look at the total time the agent takes, the number of output tokens it generates, the output, like the number of agent turns it needs, and etc. These are very concrete and also quantifiable metrics. And although we notice that there's one caveat that there is not a single metric that can show the overall agent task efficiency of a framework. And as a result, for now, we kind of need to use all these different metrics to get a comprehensive understanding of how agent task efficient a framework is. So we can now restate our central question to this one, which is more precise. Uh, can we build a framework that has both high training efficiency and high agent task efficiency? And this is the question that the whole talk is built around today. And thinking from the first principle, we want to build a system, this doesn't seem extremely challenging. We found that if we want to build a training framework from say scratch or from relatively low level PyTorch, we probably only need these components here across these three levels. At the bottom is the operator level, where the operators come from different sources like PyTorch or other fast operator libraries or customized GPU kernels. Then we have the engine level above the operators, like building blocks. They're further composed into models and also runtime, distributed training, and other distributed like infrastructure. And at the very top, it is the application layer for things like the training loop. So our takeaway is we thought that a training framework will be very complex. Well, it turns out that the architecture is very clear and we can just go for it. So we built PithTrain, and this is an overall of the whole thing. Um, on the left is the agent loop where when say a agent is working on a task, it takes action on PithTrain and also gets feedback from it. And for PithTrain in the center panel, the highlight is that we built PithTrain based on 4 different agent native design principles. Um, and also, PithTrain supports standard MoE end-to-end training and delivers both training efficiency and agent task efficiency, which we call dual efficiency. And on the right panel is the ATE bench, or the agent task efficiency bench, which we built to compare agent task efficiency of different frameworks. So let's first start with the 4 agent native design principles. And actually, to be honest, we think every of these principles is very trivial, but likely no one has seriously called them out before. So principle number 1 is compact code base, and this may end up being the most important one. Um, Having less code generally means less for the coding agent to search, fewer cross-file dependencies to track, and less for the agent to read before it is able to make sure that a change is complete. Um, it also means that with an agent that comes with, say, 1 million token context today, such as Cloud, um, it can hold the entire framework in just one pass instead of like repeatedly grabbing its way around. Although we have not yet observed such a task which the agent really needs to keep the entire codebase in its context, but this is very interesting. And on the left side is the actual architecture of PithTrain. Adding everything up, we get roughly 11,000 lines in total. Right now, it might be maybe 12,000, which is an order of magnitude smaller than the mature production frameworks that we saw earlier. But of course, this is a trade-off. We don't have the model coverage and feature coverage as good as those frameworks have. But we think if someone wants to add a feature or something into PithTrain, they should be able to like leverage agent, give it clear instructions, and then the agent can take over and add the feature or like things you need in relatively short amount of time. Okay, principle number 2 is being Python native. The benefits of uh, okay, I saw a question on sharing slides. Yes, we can share the slides after presentation. Um, okay, the benefits of being Python native are very concrete for agents. There's no cross-language interface to reason about. And also, when something breaks, it gets a Python traceback. Most of the time, the Python traceback is readable and also like pointing to an actual line. This actually contrasts the case of frameworks with heavy compiled extensions, where we ran into opaque crashes in the compiled code for multiple times. And another benefit of being Python native is, say, there is no compiled extension for us to rebuild every time we change a single non-Python line, such as C++ line or like Rust line. And because rebuilding them is a constant source of friction whenever we want to like fix something. And one thing to note is that being Python native doesn't mean we give up on GPU kernels. We don't write CUDA kernels directly, but we write our kernels in Python DSLs, such as like Triton, Taolan, and so on. So with Python DSL, we can keep the readability and a single language stack. And in the meantime, we are still able to get fast kernels. Principle number 3 is having no implicit interaction or very little implicit interaction. So on the left is the model construction pattern and Megatron. If you look at where self.mop is set up in the transformer layer, it's calling the build module with some submodule spec. But the question here is, what is that submodule? I can't really tell from here locally, and I have to go to a different file, which is the layer spec file, and trace through the module spec that actually instantiates the MOP spec. And this definition is like definitely somewhere else. And for people who are familiar with Megatron, this might be okay because they've seen this too many times. But for people who are trying to get started with Megatron and also for coding agent, this would be a lot of overhead. And on the right is PithTrain, where the definition is right there in the same file locally. Both humans and agent can read the file top to bottom and can know exactly what's going on. But actually, this is a trade-off. In PithTrain, we trade cross-modal code reuse for local readability. And we're not saying that implicit interactions are bad. The interaction on the left exists for reasons. For example, it lets many models to share the same skeleton. We deliberately give that up so that each model file is self-contained and an agent can understand the model architecture by reading one file. And this principle is not just about model definitions. It actually applies more broadly. For example, like recursive abstraction classes, and deeply nested modules, and module hooks. And these are all the interactions that we try to avoid. The last principle is task-specific agent skills. And the motivation here is a little bit different from the first 3. The first 3 principles are all about like making code easier for agent to read or understand. But we think that we just can't leave everything to reading code. Actually, there's like human knowledge, say how we actually do things, or the procedure of a recurring task. These are something that a coding agent cannot easily recover by just reading the source or calling tools. So we pack this kind of knowledge into agent skills and ship them in the REPL. But of course, this is not some novel idea that no one mentions before. However, when we look at the available training frameworks out there, we found that they don't do quite much about agent skills. For example, Megatron, it does have skills, but they're all about the CI and PR management. And Torch Titan and Torch Speed, the Deep Speed, they provide like top-level orientation files for the agent, so the agent can know about the overall project structure very quickly, but they kind of just stop there. The table on the left includes some of the skill example in PithTrain, and we are gradually like bringing more into this project. And one thing to note is that skills are composable. One skill can call another. So the one idea is you can have some like common small utility skills, and other skills will leverage them automatically. And this is actually very similar to programming, traditional programming, where we usually have some, say, common functions and also the main function. The main functions are built around these like util functions, and you can therefore treat skills as functions in natural language. In practice, we think that simply having skills are still not enough. Um, if a skill is defined too vague, then it's probably not very useful. So we identified three properties that we think are very important for designing skills. The first property is specific scope, which means we need to have narrow and unambiguous description for the skill. It's also very helpful to have some like natural language triggers, so it can tell the agents that say when you see this keywords, you run the skill. Okay. The second property is explicit prerequisite. Just as like functions in traditional programming that they cannot run without all the required input, a skill also needs to know clearly about what needs to be ready before it can execute. The key is we never want to make the agent guess. So in the skill, you can say, okay, if any of these prerequisites are not met, you just report it to me instead of like silently run the skill. Um, the last but most important one is the verifiable success. In the skill, we need to make sure that the agent can know whether it successes or like whether it succeeds or fails. For example, in this validate correctness skill, we provide a compare.py and let the agent to run this for comparison. If the Python outputs 0, it means a pass, or otherwise it means a fail. So the agent doesn't have to interpret it from the context on whether the task succeeded, but instead there's a hard-coded deterministic procedure to let the agent know the result. And another small benefit of like having programs like Python or share script for the skill is that running the script does not cost you any token. Well, if the agent tries to figure out the result by keeping thinking and costing context, it costs you a lot of token usage. And okay, next I'll hand over to Hal for the performance evaluation and AT bench.
Yes, let me share my screen.
I guess I first need to stop my sharing. Okay.
Yep. All right, I think people can see my screen right now. So coming next, I'll cover the evaluation part of the PithTrain framework, first on correctness, then the training throughput, and finally some agent-side metrics. To start with, we first validate the training of PithTrain on Queen3 30BA3B across 4 H100 nodes with pipeline parallel of 4 and expert parallel of 8. The full config is presented on the left. We train at billion token scale for this correctness check. As you can see on the loss curve next to it, we have Megatron in red and PithTrain in green. They overlap for the entire run. And beyond the loss curve, we also ran some downstream evaluation throughout the training. These are some standard pre-training benchmarks, including OBQA, Winogrand, ARCC, ARCE, HellasFog, and Pickup. As you can see, the two frameworks track each other closely. So for throughput evaluation, our setup spans across NVIDIA H100s and B200s with InfiniBand for cross-node communication. And every configuration here exercises more than one parallelism dimension at once, with PP and EP both greater than 1. From the table, you can see across the two GPU types and all three models, including GPT-OLSS, Queen's Visa DBA3B and DeepCV2 Lite. PithTrain matches the performance of Megatron, and in the one case where it trails a little bit, it's like 126K versus 124K, almost identical. The way we get these MoE training throughput out of around 11K lines of code is first via a 5-stage decomposition of each MoE layer whose execution is scheduled with the do pipe V. To give proper credit here, this builds upon the DeepSeek's do pipe for the orchestration with the V-shape variant from the C AI lab. The core idea is that for each MoE layer, we can split its execution at the communication boundaries. And in this diagram, the yellow rows here, they correspond to the communication, which are the dispatch and combine all-to-alls. And the blue rows here are the computation, including things like attention, expert MLP, and others. By breaking down into 5 different stages, this finer granularity allows the scheduler to interleave different micro batches and overlap the communication with the compute. Here is an unsys profile trace of one forward and backward pass. The agent was able to capture this on its own using our in-repo unsys profile SKU. The top string runs the compute almost continuously, and the string below runs the dispatch and combine all-to-alls. The key thing to see is that the two runs at the same time, so the exposed unhidden communication remains very small. That's the overlap behind the throughput numbers on the previous slide. So while 2pipe-V is the main optimization for this MoE training, it sits on a stack of otherwise standard techniques, including, say, a full graph torch compile on everything except the MoE because it's like dynamic shake involved. We also have the wgrad delay, so we can launch the backward of dispatch as soon as we have the input gradients of the expert MLP. We have the token deduplication before EP dispatch, and we have some custom fused kernels in various places of the training paths. So my point here is that none of the technique is novel on its own, but together they help bring a pure Python framework up to the throughput parity. So far we have covered the training efficiency side of PithTrain, the throughput results, and the optimizations behind them. It corresponds to the left side of this figure. But training efficiency is only one axis. The right side is the second axis we want to evaluate, agent task efficiency. In other words, how efficiently a coding agent can understand, operate, and extend the framework on its own. Intuitively, our agent-native design principles should be helpful here. But rather than just asserting things like a compact codebase is more agent-friendly, we wanted to measure it directly in an empirical manner. And that's what ATE Bench is designed for. The setup here is kind of inverted from a normal coding benchmark. Right? In things like SWE Bench or Human Evolve, you fix the codebase and the task, but vary the agent in order to score and rank the capability. ATE Bench does pretty much the opposite. It fixes the agent and the task and vary the framework so difference in the agent efforts is attributable. In other words, it's somewhat complementary to those capability benchmarks. Before we get into the specifics of ATE Bench, I think it first helps to think about how we as a human work with a training framework in our daily usage, right? Because that's what these tasks should be built around. And to be honest, our level of involvement can vary a lot, right? Sometimes we may pull up that GitHub page, maybe read some command line arguments, hunt for that one file, like trying to answer whether something is supported or not, like a question in our mind. We're trying to look at the file and just to find the answer. Sometimes we can run the codebase settings. So for instance, Megatron may provide some training receipts, and we may just train a model using the provided receipt without any modification of the framework at all. Sometimes we may go invest all in, extend the framework ourselves. We may like read some latest published papers and do some modification of the framework in order to test out a new architecture and getting it to train end to end. ATE Bench mirrors exactly these three levels of participation. It has these three different tiers, and the agent's roles deepens across them, from first a reader to a user, and finally a developer. So in the first QA tier, we ask the agent to like answer a question about the code. For instance, it can be asked like, how is the device mesh built? Like, how does these parallelism dimensions compose together? It doesn't have any runtime measurement. It's mostly locate the relevant code, read through it, and explain the answer using tools like grab and find to navigate the codebase. The output is just an answer to the question we ask. In the second operate and profile tier, the agent runs and perhaps instrument the framework. For example, it can capture an ANSYS profile and run some analysis. It configured the run, it launched the training, and it analyzed the results. The output can be some quick report or some training artifacts. In the final and perhaps the hardest tier, we have the new feature category, where the agent ports a model architecture end-to-end against a published reference. For example, we have the mixture of block attention. It's a change with the attention mechanism, where when the agent tries to pour this architecture into the framework, they need to explore the codebase, implement the feature, test the changes, and debug any errors along the way. The output should be a verified working code integrated into the framework. Specifically, in our setup, we use Cloud Code as the fixed agent, and we use Opus 4.7 at its extra high level of effort. We run each task 3 times independently and report the median of the metrics. At this extra high level of effort, we found every task passed on every framework, so we can have a clean comparisons that focused on efforts alone. So here is the result from the first level of category on the QA tier, where we have curated 12 different questions focusing on topics related to a training framework, including, say, how does a config gets propagated, how does a kernel gets dispatched, how does a role gets implemented inside the codebase, and many others. For each one, we report 3 metrics per framework, where lower is better, including agent terms, per turn context, and the output tokens. We never report the workload time for QA. That's mainly because each answer only takes about 2 to 3 minutes to complete, and the server load can vary between the runs. Using the physical workload time would be inaccurate in this category. Across the 12 different questions, the agent uses up to 67% fewer terms on PithTrain than on Megatron, with output tokens dropping in the same way. Torch Titan is usually the second closest to us, consistent with its PyTorch native design for rapid experimentation. So these results come from the 2 principles that we discussed earlier. First being a compact codebase, and second being the absence of implicit indirection, both of which can shrink the search space the agent needs to look at, so the agent can reach the answer in fewer terms, and they can read less at each step. We also have the results from the operate and profile tier, where now the agent is running the framework. We also report in minutes the session duration and active GPU time. So we have 4 different tasks over here. The getting started, just set up the environment. You have the framework available. You need to install all the dependencies. The train and evaluate, it drives the full, like, train the model, exploit checkpoint, and evaluates, like, with some LM evaluate harness, this entire pipeline. The collect routing trace kind of instrument the training and dump the per token expert IDs and the gating weights, which can be helpful if we want to track the expert behavior over time. And finally, we have the report heavy kernels task, which profile a run against ANSYS and report some long-lasting CUDA kernels. And we found that PithTrain is the best line in nearly every role on getting started. For example, the agent turns drop from 88 to drop from 88 on Megatron to 26 on PithTrain, and the session duration drops from over 40 minutes to under 7. In aggregate, the agent terms fall up to 70% versus Megatron, and 57% versus Torch Titan, with output tokens dropping even further. I think an interesting tell from this is the report-heavy kernel task, where the agent can invoke our in-repo unsafe profile skill on its own, running a fixed verifiable procedure instead of building the profiling workflow from scratch. Finally, we have the results from the new feature task, where this is perhaps the hardest one. The agent needs to port a new model architecture end-to-end into the framework. And to keep it balanced here, we kind of pick 2 features that change the attention, including differential transformer and mixture of block attention, and 2 others that change the FFN, including DynMoE and MoE++. This exercise the full loop of editing, running, testing, and debugging. And across these tasks, the iteration cost measured in active GPU time is up to 44% lower than Megatron and 64% lower than Torch Titan. We found the cause is oftentimes where the errors surface and how many training reruns the agent spends recovering from these errors, because each rerun, they cost GPU time, and the patterns we found differs by the framework. On Megatron, for instance, and there are 2 patterns. First, the agent sometimes manually added the CLI flags that can collide with an auto-derived transformer configs. It's hidden in the argument registry. That's kind of an implicit indirection where the conflict isn't visible when the agent first reads the code. It only surface back to the agent when it launched the training and it crashed. Secondly, we also have some C++ modules like Transformer Engine integrated into Megatron. And when the agent tries to modify its calling, they can throw some opaque seg faults. Instead of having a Python traceback that can directly pin down the errors, this opaque error message, it can push the agent into speculation, like where does this error occur? And sometimes the agent may attempt to propose the fix that is not directly fixing the error as a result of this speculation. On Torch Titan, some of these reruns we found are commonly related to out-of-memory debugging, which is a runtime property and not a matter of Codebase structure. A fair question to ask here is like, how much of this work is just compactness and whether the skills could help on their own? Like, skills are perhaps one of the 4 principles that we can ablate very cleanly because they are self-contained files and we can toggle them on and off against an otherwise identical codebase. So we run the ablation here on the wgrad delayed commit with 2 different skills. On the first, validate correctness, and the second, capture unsafe profile. This kind of mirrored the natural follow-up to an optimization, where we validate the correctness first and then profile the performance. We ran each task 3 times with the skill and 3 times without it. When it's off, we remove the skills from files everywhere, including the working tree, the Git history, so the agent has no access to them and can't recover the procedure. So from the table, we do see some expected results. The active GPU time stays flat. I think here the nature of the task will kind of pins down the fixed set of training runs. So the GPU work, it doesn't increase depending on like whether the skills are available or not. But the agent side metrics, like including per turn context and output tokens, as well as agent turns, if you take a look, they drop very sharply. On validate correctness, for instance, the agent turns go from 114 down to 34, and the output tokens drop from 30K to roughly 11K. So with the procedure in the skill, the agent runs a fixed plan instead of re-deriving one by trial and error. And as a result, the same GPU work gets done with much less agent effort. To make the whole things concrete, let me walk through one case in detail with integrated MOBA, where we specifically break down the agent effort by its action category. We look at the transcript and we classify like different actions. There is one little caveat here. We do omit the thinking tokens from here because the cloud code redacts them away from the transcripts, so the analysis here pertains to only what's visible to us. The left panel shows the output tokens by activity. For instance, on editing, PithTrain uses 4.7K tokens compared to 13.1 tokens for Megatron and 22.2K for Torch Titan. The change stays local, so less code is needed to land the same feature. On exploration, for instance, Megatron spends 10.2K tokens navigating the codebase versus 2.2K for PithTrain. That's the compactness and no indirection effect. The right direction, we also plot the per turn context over 3 independent sessions for each of these framework. And as you can see, PithTrain in green stays low and flat throughout. So that concludes everything we have on the evaluation part of the framework. I'll hand back now to Ruihang for some of our future work and the broader discussions.
All right. Let me share my screen again. I guess it's mainly some open discussions that we think is very interesting to the community. The first one is the importance of agent task efficiency that we introduced. We really want to know like how much do people really care about this idea. One thing we know is that industry people are rich. In industry, almost no one will actually worry a lot about the token usage. They even encourage people to use more token. So if if completing a task saves you some token, that's not very appealing to industry people. The second point is like we show some AT differences between PithTrain and other baseline frameworks, but the differences we saw are not significantly large enough. For example, we have a 10 time more than 10 times smaller code base than other mature production frameworks, but our agent task efficiency, if you look at the numbers, we are not say more than 10 times better than them. At the end of the day, it could be say completing a task on PithTrain takes 2 hours, and on their framework takes like 3.5 hours. That's not significantly large enough differences. So this is also something very interesting. And the third is that we all know that the agents are keeping evolving. They might be even better, say, in another year. So right now we can see some differences, IT differences between different baselines, but we don't know what the case would be after 1 year. It might be a case that okay, agents are even more powerful at that time, and there is almost no observable AT differences at that time, but it could not be that case as well. So we don't know the result. But on the other hand, I think one thing we have been observing is that the ATE thing is becoming something that agent people may care. Just like, for example, like in this screenshot, this is a pull request from the Megatron LM that adds experimental Megatron Light as agentic exploration. So they do want to have some also build something for agents, more friendly for agent, and at least this can show that ATE is getting some attention from the industry people. Okay, for other discussions, the first one would be as how introduced in the ablation section. ATE is still not crystal clear. At this moment, we can only ablate the agent skills, but what about the other principles? We really can't tell, say, how much do the compactness contribute to the result, because if we want to ablate that, we kind of need to add the code base from say 11K to over 100K, and there is no way to add code that can add code elegantly and then do the evaluation. So we still need to. I think we need effort from the community to try to understand better, get a better understanding of like how do each of the factor contribute to the ATE, and also in this talk in PithTrain we named 4 different agent native design principles, but these are not everything. We do believe there are other factors that are also very important and can contribute to ATE, and also this needs effort from the community. Um, Moving on, the task selection in ATE bench is something very interesting because we kind of need to in ATE bench we need tasks that are not supported by all the baselines. The reason is because if, say, I want to evaluate a task, evaluate a framework on a task, where the frameworks actually has already supported the task, then it makes no sense to use the task. It's unfair. So this means that the AT bench itself also needs to evolve across time, because some of the existing tasks might be outdated. Uh, Say when some framework supports it. So we need to keep having new tasks and removing some of the old tasks. And lastly, the development of PithTrain is saying that we are not freezing the code base right now. The PithTrain also itself needs to evolve. The code base we know always grows, and maybe it will become, say, to 20,000 after 2 months and even larger. But the only thing we want to make sure is that we want to control the growth of PithTrain, and we want to make sure that it grows in a way that like aligns to our design principles. So this concludes the discussions, and finally, um, this is like the whole thing of PithTrain and AT Bench. We built PithTrain that is built around 4 different agent native design principles, and it delivers dual efficiency. We also have AT Bench to evaluate the agent task efficiency. And here are 2 different triples, so one for PithTrain and one for AT Bench. Finally, huge thanks to all the collaborators that make all of this happen. And yeah, so that's it. That's everything, and we're happy to take any questions.